Okay, students, let's dive into Chapter 14, Oscillations. Let's look at equilibrium and oscillation. Okay, now you should be somewhat familiar with what we mean by equilibrium position or what it means to be in equilibrium. If you've ever had chemistry, I know you did a lot there with reactions. Are they at equilibrium or not? What type of reactions will stay at equilibrium and those that will continually go back and forth and so on. Okay, now, well, if you recall from first semester physics, we covered Hooke's law, and we're going to kind of come back and touch on that a little bit more. And we talked about the equilibrium position of a mass on a spring. All right, well, all right, we're back at it again. So what do we mean by equilibrium position? Well, typically what we mean is that at equilibrium position, typically what we mean there's no motion. Notice it's sitting here, resting still. And if we move this ball through this curved surface here, looks like the bottom of a bowl. If we pick it up here, we know, and I do not know what happened there. It's going nuts on me. Okay, now, all right. So if we pick it up, and pick the ball up and put it here, we know it's going to roll down this way, and it will roll back and then back and forth and back and forth till it eventually comes to its equilibrium position due to gravity. Well, what causes that are what we call the net forces. Of course, you have a normal force always acting on it, and then of course you have the force of gravity, or what we call weight, acting on it. Now, this force that causes it to return to its equilibrium position is called the restoring force, okay? So that's what causes the ball to go back to its equilibrium position when we move it. Now, needless to say, as the object is moving, it does have a velocity. And of course, when it's at equilibrium position, it has zero velocity, but when you release it from this location or from this location, it will have an initial velocity, and its velocity will increase, okay? So it has changing velocity, therefore it has acceleration. Now, this repetitive motion is what we call oscillation. Some of you've probably watched maybe a pendulum swing on a clock, or maybe if you've ever seen one of those law of conservation of momentum apparatuses where they pick the little ball up and drop it and it hits the other four and one comes up off the other end. It seems like it's oscillating back and forth. That's an oscillatory motion too. Now, oscillation is always going to have a frequency. It's characterized, or it's identified by its frequency and or its period. So how do we define period? Well, we've actually already talked about this. We'll talk about it again in last semester. Period is the time it takes to complete one full cycle, and of course the units are going to be in what? They're going to be in seconds, okay? Typically that's the way we define the units for period. We could, according to what you're talking about, like if you're talking about the period of a planet around the sun, then we would probably do it in Earth days or Earth years, okay? But generally speaking, for studying wave motion, oscillatory motion, we're going to put our periods in seconds, okay? Then the difference in period and frequency, notice that frequency is the reciprocal of period, and basically what it is, it's the number of cycles that occur in 1 second, okay? So if you have 60 cycles per second, then that means that the oscillation of the device, whatever it is, does 60 cycles, which is one complete cycle. What is one complete cycle? Well, typically we just define it as 360 degrees, okay? That it returns to the starting point, okay? It goes all the way around, comes back to starting point, okay? Starting position. So that's what we call a period. One cycle, so the number of cycles in a given time period, which is 1 second, is frequency, and the unit for that is the Hertz, named after Heinrich Hertz. And of course the guy that's responsible for radar, or his discovery led to radar. Now we can write it Hertz or we can write it reciprocal seconds. It is the same thing, okay? So how do we find the frequency from the period? Just take the reciprocal of the period. Or how do we find the period from frequency? Take the reciprocal of the frequency. So it's very easy to find. That's not the only way we can find frequency and period, but these are the easiest ways, okay? So if we graph oscillatory motion, notice that it is sinusoidal. Notice that if we start out here and we graph this motion, this ball as it is moving with a given velocity and acceleration, notice if we start out graphing it, notice it is sinusoidal. Notice it starts here at the highest position, it moves towards 0, then notice the direction, it begins to move more negative, and the negative direction, what do you mean negative direction? It's going the opposite direction. It's going this way, all right? It's going up instead of going down, okay? And so notice then when it gets back to 0, notice where it is, boom, right there at 0, okay? And then back to its highest position, boom. And so once we complete one cycle, that is 360 degrees, okay? Okay, here's 90, there's 180, there's 270, and there's 360 right there, okay? Okay, all right? And we call this motion a motion that is repetitive, sinusoidal oscillation is also referred to as simple harmonic motion. So anytime you have a motion that is continually repeating itself, then it is considered to be simple harmonic motion, okay? Now, linear restoring force. Now, one thing we need to understand about simple harmonic motion and objects in motion, oscillatory motion and simple harmonic motion, you're going to have what is called a restoring force. Now, here we kind of regress, go back to Hooke's law, and of course we know that Hooke's law is very easy to work with. We have the Hooke's law constant, and of course that's what we call the spring constant, isn't it? Yeah, that's the spring constant. Okay, now notice the negative there. The negative sign tells us that the restoring force is in the opposite direction. That's the only reason that negative is there. It is not a negative spring constant. Okay, spring constants are not negative. Okay, it just tells us that the direction of the restoring force is in the opposite direction. So what does that mean? If I take this block and I compress it, or if I push it, either way, if I stretch it this way, the spring restoring force is in the opposite direction, okay? That's all it tells us. So if we move from the equilibrium position, which is right there, and we move it delta x, a given displacement, okay, then guess what? The restoring force is going to pull it back in the opposite direction. Likewise, if we compress it, it's going to do the same thing, okay? So a linear restoring force, of course, is the net force is always towards the equilibrium position and is proportional to the distance from the equilibrium position. Well, look, y'all, can you not decipher that from the equation? Sure you can, okay? As Jethro would say, we need to cipher, don't we? Okay, absolutely. So you can tell mathematically that it is proportional to the restoring force, or is in the net force, and it's proportional to the distance from the equilibrium position, okay? So net force is always in the direction of the equilibrium position and is proportional to the change in displacement. Now, what is amplitude, however? Okay, now amplitude is similar to displacement of the object as far as how far we move it, but amplitude is the maximum displacement from equilibrium, okay? And we define that with a capital letter A. Very important. I hope you're writing these equations down, and I hope you're writing these symbols down. Very, very important, okay? So oscillation, anytime we oscillate about an equilibrium source with an equilibrium position with a linear restoring force, it's always simple harmonic motion, okay? I like they put these bold black and black bold print statements to sum up what we're talking about, because those are good little things to remember, all right? It sums it up for us in one sentence, okay? So in other words, what do you mean by amplitude? Okay, so if I pull this string out and stop and let it go, then guess what? It should not ever go beyond the maximum displacement or the amplitude that I set for that particular series of motion, okay? Now, what about if we hang it vertical? Well, y'all, nothing really changes. The only thing that changes, instead of saying X, we say change in L. Well, y'all, L is length, okay? It's the same difference. It's still displacement, okay? So don't let the changing from delta X to delta L throw you. Y'all, it's still changing displacement, okay? They're just saying the length of the spring. Okay, well, that's still displacement, okay? And so guess what? Our equation then is going to be what? The same thing, except instead of delta X, It is delta L, okay? Not a big deal there, all right? So then if we look at, since gravity is acting on the spring and causing the spring to come down towards the surface, then we can write this equation right here to find the length of the spring at equilibrium position based on the object's mass and the spring constant. So that's a very useful equation there. If you have a spring, you say, okay, what is the change in length of the spring going to be at the equilibrium position? Well, boom, you know the mass of the object, you know gravity, 9.8, and then if you know the spring constant, there you go. You can find it. Or if you want to find the spring constant based on, look, so you can write it this way. Spring constant is equal to mg over what? The change in length of the stretched spring. So you say, okay, I know the mass, I know the g, I know how far the spring stretched, but I want to know my spring constant. Well, there you go. That's how you find it, okay? And that's how they are found. That's one way we can find them, okay? All right, now, that's a simple way to do it. So, again, the vertical mass on the spring, look at here, Hooke's law, boom, 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 all right? It's really all it is. It's just Hooke's law tilted up, okay? No big deal, all right? Okay, now, all right. So, what does gravity do? Well, of course, gravity is the force that acts on the object, and of course, the spring tension is what we call the restoring force. So, even though it's vertical, it still has a linear restoring force, even though it's vertical, okay? And it still oscillates with simple harmonic motion. So, just because you go from horizontal to vertical doesn't mean you no longer have harmonic motion, okay? Okay, all right, I hope this is helping. So how do we define a pendulum? Well, I think most all of you should know what a pendulum is. Most of you have probably seen a pendulum clock in someone's home, or you maybe when you did work, did particular labs in physics or physical science, you did a simple pendulum. You can really teach, there are several principles of physics you can teach from using a simple pendulum. You can teach gravity, how to calculate gravity. You can teach how to solve for the period. In other words, if I want my pendulum to have a certain period, how do I do that? And you can even find the mass of the object too. All right. So there's several different physical principles that you can learn from just a little old simple pendulum. Okay. All right. So how do we find then the net force on a simple pendulum? Well, if you take your simple pendulum and you start drawing draw it out and draw the equilibrium position, which is there. Notice you've got an angle, you've got an arc length, you've got the actual length of the pendulum. So how then can we find the force, the total force? Then we use what? Negative mg sine theta. Why negative? Again, because of the restoring force, okay? All right. So we can find it that way. You can also find the weight using that equation. Now, all right, so since the equation is simplified for small angle, or what we call small angle approximations, then we can do what? Then we can say the force net on a pendulum, or the tensional force, is equal to what? It's equal to negative mg over L, okay? So if we take away the sign and we say, okay, we're going to look at small angle approximations here, we're going to take that away. Then since they're proportional, sine theta is proportional to theta, then we're just going to calculate it this way. Boom, right there. So we take the force of gravity, which is causing it to move, the length of the pendulum, times the arc length, S, then we can find the force net. So there's another equation. You can calculate. This would be our the force, the net force on a simple pendulum, okay? So that's how you would need to label it, all right? Okay. And of course, simple pendulums do undergo simple harmonic motion, okay? Now, this gets very kind of detailed here. They're going through the different phases of a simple pendulum here, or simple harmonic motion. And notice they're describing the position graph, the velocity graph, and the acceleration graph. Now, what I want you to notice here, notice there's some correlation here. Notice where you have zero, notice where you have when the object is back at, notice right here. Now, y'all, I'm not going to read all this to you. You can read it. I'm going to kind of summarize it, okay? Notice right here that when the object is at the equilibrium position, when it is back at zero, okay, When it's at 0, notice what the velocity is. Velocity is maximum. Do you see that? Do you see that correlation? See right here, where when we get back to equilibrium position, all right, so when we release it, when it gets all the way back, when it gets down to its equilibrium position where it's not going to stretch anymore, notice that we are at what? Zero displacement, maximum velocity, and look, 0, so you have y is 0 meters, velocity is maximum, and notice that acceleration is 0. Now you say, well, how can that be when you got maximum velocity? Because remember, y'all, if you remember from Newtonian, when we studied in 201, when you achieve maximum velocity, velocity is no longer changing, therefore you can't have acceleration. Okay? You can't have acceleration. All right, now, so what's going to happen? Well, the object is going to start moving now in the other direction. Okay? So notice right here, where you have maximum displacement again, notice what velocity is. Okay? Now remember, here's equilibrium position. Boom, right there. You say, how do you know it's equilibrium? Because it's 0. All right? Look, when you have maximum displacement, look at your velocity. Boom. It's 0. You see that? And they're telling you this over here in the margins in the printout here. See, look, boom, maximum displacement, 0 velocity, but now wait a minute, you got maximum acceleration. Well, you say, well, now wait a minute, how can you have 0 velocity and have maximum acceleration? Well, because the acceleration now is starting to go back in the opposite direction. And so there we see it. Notice, equilibrium position, max velocity, 0, boom, boom, boom. Okay? So I love these graphs because it shows us the progression of an object in simple harmonic motion, and it relates position to velocity to acceleration. So and they tell you this over here, so when position is 0, velocity is maximum. When velocity is maximum, acceleration is 0. Okay? All right, and then they go on and tell you that in the rest of these slides. I'm not going to read to you, okay? All right, okay? Notice they talk about when it's reached the turning point, okay? Okay? So the net force is upward, acceleration is positive. See, that's what I was telling you just a minute ago, okay? All right, and then you can read on. I'm not going to read to you, okay? I'm not going to verbatimly read to you. Not all that anyway. All right, so then let's describe this motion that is simple harmonic, and it's, of course, oscillatory. So we can use to find the displacement during a given time interval. We can take the amplitude cosine of 2 pi t, all right, over the period, okay? Over the period. And of course this indicates that it is a position, is a function of time. In other words, we actually have a derivative here. We can actually take a derivative of this, and here in a minute you'll see the derivative. So the cosine function can be written in terms of frequency. So we need to write this down, okay? So the amplitude cosine of 2 pi, the frequency times the actual time interval for that particular moment in time, okay? That's not period, that's like 5 seconds. Where is x? Where is the position of the object in simple harmonic motion at 5 seconds, okay? That's what we're talking about, okay? All right, so we can then take this equation and take the derivative of displacement, and notice that the derivative of cosine is what? The derivative of cosine is what? Negative sign, isn't it? Now you say, oh, I didn't think we was doing derivatives in here. Well, I'm not going to make you do them. But y'all, this is where it comes from, okay? All right, so you take the derivative of cosine, you get negative sign, don't you? And so then we can simplify. Now notice at max, velocity max, what is it? It's negative times the negative velocity sine of 2 pi, a frequency times the time interval for the particular, for that particular time interval, okay? All right. And then, of course, the restoring force is what? Well, it's that right there, y'all. Force net, because where'd you get that? Well, look, y'all, force is equal to MA, so A is equal to what? A is equal to the force over M, right? Sure it is. Okay? And the force is what? Well, the force is Hooke's law. Okay? The force, restoring force in that situation is Hooke's law. Notice the negative, the K, and the X. All right? So that's what the restoring force is there. So then the acceleration. Now look at here. Now how do we get this equation? All right? Well, again, we take the derivative of this equation and notice what we get. Okay? Well, what is the derivative of sine? Well, it's cosine. Okay? It is cosine. So the derivative of sine is cosine, and so notice what our equation becomes. Okay? All right. Okay. So I hope you've written these equations down. You write all these down, okay? You need to write every one of them. Of course, you already know that one. And if you don't, you can still write it out. Okay? And then this one, okay? And that's acceleration max, okay? All right, now. And again, they're just summarizing it for you, okay? All right. All right, so what about uniform circular motion? Well, believe it or not, uniform circular motion is also harmonic motion too, okay? All right? When it's in one dimension, it's simple harmonic motion. You mean to tell me an object on a turntable is simple harmonic motion, or something going in a circle? Yeah, it sure can be, okay? And so we can take this and we apply our angular frequency equations and do some substitution here. And notice that instead of saying what? Instead of saying frequency, we say angular velocity or angular frequency. Okay, and we substitute into the equations, and notice what it becomes. Notice that displacement along an arc is what? A cosine phi. And what is phi? Well, if you remember from when we studied last semester, it is the angular velocity times the time. Okay? All right, and so now let's look at these equations. So for circular motion, notice that to find the x component during a given time interval, notice what it is. Notice it is the amplitude cosine of 2 pi f or t. Well, boy, that's real similar to the other equation, isn't it? Well, it sure is. Okay? All right, so as we progress through, then guess what? Well, gee, if I take the derivative of this one, then notice what it becomes with respect to time. Notice what it becomes. Well, gee, it's going to become negative 2 pi f times a sine of 2 pi ft. All right? Or if we just want to find the maximum velocity, you say, well, why maximum velocity? Well, when the sine is, when it's at 90 degrees, the sine of 90 is what? 1. And so that's when velocity is at maximum, when you have a 90 degree angle, okay, when it's at 90 degrees. All right? Okay, now, and so you can write it this way, but now this is just for the velocity of the x component of an object in uniform circular motion. But if it's at maximum velocity, you can drop off all of that, and it is what? It's what? 2 pi f times a. Okay? All right. Then, guess what? We can take the derivative of that, and notice what it becomes. It becomes negative 2 pi f squared times a cosine of 2 pi f. And again, if we are at maximum, remember, what is the, now where's acceleration maximum on the cosine side? Well, it's a maximum at 0 degrees, isn't it? Because the cosine of 0 is what? 1, right? 1, okay? And so then it all becomes what? It becomes 2 pi f squared, okay? All right. So make sure you have these equations. That's the acceleration of the x component, and here's the maximum acceleration. All right, so write these down. And again, here they're just describing it to you, showing you position, velocity, acceleration, and how the equations relate. Okay, and again, I'm not going to go over that. You can read it, okay? All right, what about energy in simple harmonic motion? Well, guess what we're going to do, y'all? Guess what we are going to do? Well, we know that energy, notice that at this position, when it's stretched as far as it will go, it is complete potential energy. In other words, here it's at the motion is 0, okay? So here we got what? Velocity is 0, okay, at that position right there, okay? It's at 0. Now, so we don't have any kinetic, do we? Well, of course not. But what we do have is potential, all right? We've got elastic potential energy. Notice they show you here when it's halfway in between, you've got purely kinetic. Then when it's completely compressed, and you say, well, I say halfway in between. You say, why is it halfway in between? Because here's the equilibrium position. That's equilibrium right there. That is zero. That's equilibrium. And so guess what? You're at max velocity, zero acceleration. So there it is totally kinetic. And then when it compresses and gets all the way back over here, guess what? Now you're back at purely potential. So we go back and forth and back and forth. All right, you follow me? So let's put those together. So the sum, the total energy, should be what? The sum of the kinetic and the potential energy, shouldn't it? Sure it is. Now here they tell you when it's what I just told you, okay? I just told you this is what it is saying. When the equilibrium position, the kinetic energy is maximum potential is zero, and then of course vice versa. I just told you that, okay? So let's put this together then. So if we take the total energy, it's going to be equal to the kinetic energy plus the potential energy. It has to be both, okay? And yes, they do add, okay? They are additive, all right? Now, so we know then that from our Hooke's Law chapter in last semester, 1/2 kx squared is the potential energy of a spring, an object stuck to a spring. So we know kinetic energy is 1/2 mv squared. So they should add together and equal a constant. In other words, they are constant to each other. So when we want to find maximum displacement, then how do we do it? Okay, well, we're purely potential, okay? Purely potential. Now again, let's back up. Let's look at our equations here. Notice that they changed the x to a. Well, big hairy deal, okay? Big deal. All right, so there it is, okay? And so when we are at maximum displacement, it's purely potential, so the only thing we have is that right there, right? Okay, because there's zero kinetic. But then, of course, when we are at equilibrium position, it's purely kinetic. And so we have zero potential, right? Okay, all right, okay, and that's just showing you the breakdown. All right, so since we have conservation of energy, then we can set them equal to each other and find what? We can find the maximum velocity. Since energy is conserved, we can set kinetic equal to potential, and we solve the velocity maximum. And here you need to write this down. This is for an object in simple harmonic motion on a spring. Okay, please write that down that way. Okay, because you say, how do you know that? But look, there's Hooke's constant right there. There's the spring constant, the mass, and then the amplitude. So please be sure you write it down that way on your formula card. So when we earlier found that it was this right here, didn't we? Velocity was this. So if we want to find then the frequency, okay, if we want to find the frequency, see, look, what they do, they took this equation and set it equal to that one and then solve for frequency. Notice it's 1 over 2 pi times the square root of k over m. And if you want to find the period, then look, then it's not 1 over 2 pi, it's 2 pi times the square root of m over k. Notice how everything flips, doesn't it, okay? So please write these down. And again, these are, notice it tells you, now I like how they annotate these, how they annotate these things. Notice right here, come on, pen, work. Notice, all right, it is for an object that is in harmonic motion that is on a spring. A mass on a spring. Please write them down that way. Okay, so the frequency and period of simple harmonic motion are determined by the physical properties of the oscillator, no duh. So if you have what? If you have stiff spring, low mass, you have a high frequency. If you have a soft spring, high mass, you have a very low frequency. Well, duh. I mean, come on, y'all, look at your equation. I don't need to tell you that. You folks are math geniuses. Look at it, okay? Look, it's inversely proportional, isn't it? It's inversely proportional to the mass, but directly proportional to the spring constant, right? Sure it is, okay? So the frequency and period are not dependent on what? Oh boy, they are not dependent on amplitude. That's a tricky part sometimes. We do this lab in my Cal-based physics, and some of them think, oh, it's the amplitude, it's how far we stretch it. No, if you do it right and just look at what's going on, you can see very clearly that it's the mass, changing the mass of an object on a spring that's going up and down. It's obvious that it is the mass. Notice that amplitude is not anywhere in that equation. Nowhere, okay? Well, this is a constant, okay? So it has to be based on the mass. All right. And again, then there's just some more there summarizing what we've already talked about. All right, and then we look at pendulum motion. All right, so we have pendulum motions. We actually have two kinds of pendulums, simple and a physical pendulum. All right, so notice that the tangential restoring force, what we was talking about earlier, is what? Is proportional to the object's mass times gravity and inversely proportional to the length of the spring. So again, to find the tangential restoring force, and again, what is tangential? Tangential is going to be that right there, tangential, okay, the tangential restoring force is what? Okay, is proportional to the negative mass divided by the L times the arc length. And again, we're doing small angle approximations, so we don't have to use sine theta. All right, okay. And so pendulum motion can be defined this way. We can find the arc length by doing what? Well, just do some substitution here, and we can find the arc length by doing what? A cosine of 2 pi f of t, or we can find it this way, that the arc length of tangential motion is equal to the arc max, which is cosine of 2 pi ft, okay? And again, you say, why are we looking at this? Well, we are looking at the length of the pendulum. That is a constant. So what does this mean? If we have a short pendulum, we're going to have a high frequency, see, inversely proportional. We have a long pendulum, we're going to have a low frequency, okay, inversely proportional. All right, that's what they're trying to get you to look at there. They're trying to get you to use your algebra and look at your proportionalities there. And so we can do this pendulum motion. Notice that it's not very different. Notice what swapped places. Notice right here. That was K, wasn't it? And this was what? What changed? The mass, wasn't it? Yeah. So notice how notice this now. I'm making a point here. Notice how the frequency of a pendulum and the period of a pendulum is not, it is not dependent on mass. Now, if you have a spring in harmonic motion, then it is. But here we just have an object hanging from a string or a wire or whatever. Notice that it is not dependent on mass. Well, why? Because of gravity, okay? All right, gravity acts the same on any object, no matter if it's 100 grams or 1,000,000 grams. Gravity acts the same on both objects, okay? Remember, Galileo proved that, okay? All right. So notice how the only change was, this was K, now it's G. This was mass, and this was mass, wasn't it? It was, but now it's L, okay? And we're talking about a pendulum now. We're not talking about a mass on a spring. We're talking about a pendulum, okay? All right, so I just want to show you the correlation there. All right. So it is not dependent on the mass. That's what I just told you, okay? That's what I just told you. All right. All right, so what is a physical pendulum? Well, a physical pendulum is where you have a mass is distributed over the length of the pendulum. In other words, it's distributed over the entire length. And here we have to find what is called the center of gravity to find the actual period and frequency. And so what we end up doing then is we do a little bit of modifications here. Notice that mass does come into play here, but you know what? Right there we see that the moment of inertia comes into play too, okay? So we do have to consider the mass. Why? Well, because we have to find the center of gravity, the center of mass, okay? And so notice the subtle change in the equation, but notice how these relate into constants, okay? That is what's going to change, okay? Well, actually the mass, this is constant, G is constant, okay? All right, folks, and that's it, and I hope that this helps.